Hello, Paul 251 students. We are going to start our first lecture on probability theory. So, as a starter, at the start of this semester, way back in late January, early February, I talked about the characteristics of political science knowledge. And one of those aspects that I had mentioned is that political science knowledge is probabilistic. So what this means is that everything that we see in our day-to-day world, all of the political phenomena we're trying to understand, doesn't come with 100% accuracy or certainty. There's always going to be some type of random chance involved. So when we think about things like how people vote in elections, or whether or not a country is going to be facing civil war, or whether a policy is going to be successfully enacted, those things aren't 100% yes or no. They don't come with 100% certainty. There's probability baked into those things, just like if you were at a casino playing craps or roulette. So knowing that random chance can seep into any human behavior, we need to figure out a way to measure it. We need to figure out a way to account for it. And this is where political science starts to think about probability. So political science can make causal conclusions about behavior. We saw this when we talked about experiments and talking about relationships between independent and dependent variables. So political science does this. We make conclusions about the world, knowing that every single event that we experience in our day-to-day life and in our political world comes with some element of chance. Now, how do we do this? Well, the reason we can do this is because we can quantify the actual amount of chance or this kind of error that we see in the world. I talked about this when we talked about political polling, and I called it the margin of error. I also talked about this when I talked about random sampling error, and I talked about how we draw samples from a population. So we already are talking about these things. We talk about them as random sampling error. We talk about them as margin of error. So this is basically how political scientists quantify the fact that random chance and just chance in general seeps into our political phenomena. What we're going to do here in this lecture today is actually talk about what the quantity of chance is. Actually start talking about probability. And the first question here is, well, what exactly is probability theory? And probability is the study of chance associated with the occurrence of events. So the general notation here that we're going to see is the letter P, or the letter, big letter P, small letter R, and then in parentheses, an outcome. So basically what that notation is saying, what is the probability of a certain outcome occurring? Now this outcome could be, say, Joe Biden getting the Democratic presidential nomination. It could be the probability of the sun shining tomorrow. It could be the probability that a new drug intervention works to lower blood pressure or whatnot. So in probability theory, the general equation to get a probability of a given outcome has a numerator and a denominator. In our numerator, it is specifically the number of times an outcome can occur, and the denominator is the total number of times that any outcome can occur. So let's think about this in terms of a really simple example, say a coin toss. So we have a coin, it has heads, it has tails. And say I want to figure out the probability of heads. Well, our equation here for probability, its numerator is the number of times our outcome can occur over the total number of all outcomes. So with our coin, we have two potential outcomes, heads or tails. That's our denominator. And our numerator is 1, because heads is the only outcome we care about. So in this case, the probability of heads is 1/2. Heads out of heads or tails. Another example, let's think about a die. Say again, like you're playing craps or whatnot at a casino. You have a 6-sided die. And what if you want to know the probability of rolling a 6? So here, if we think about our probability equation, our number of outcomes that occur is only 1. We only care about seeing a 6. And the total number of outcomes that can occur are 6. So on a 6-sided die, we can observe a 1, a 2, a 3, a 4, a 5, or a 6. So when we're thinking about the probability of rolling a 6, that probability is 1 out of 6. So let's cover some other basics. All events in our world have probabilities. And the probability of event A, which that's just a notation for an event occurring, just like I called independent variables X's and spurious relationships Z's. We're going to call events A. So the probability of any event occurring is written as the probability of that event. So probability of event A is written as PR parentheses A. Now, when we think about probabilities, this isn't just a one-shot deal. This isn't just me flipping a coin one time or rolling dice a few times. When we think about probabilities, this is over an infinite number of trials. When we have this equation for probability, this is the probability that an event occurs over the long run under similar circumstances. So if I were to flip a 2-sided coin an infinite number of times and record when I get heads and when I get tails, or if I were to roll a 6-sided die over and over and over again and record how often I get a 2, a 3, a 4, a 5, it's the probability of that event occurring over the long run under similar circumstances. So for all probability models, we're going to need a description of all possible outcomes. Again, so if we have a 2-sided coin, knowing that our outcomes are heads and tails, or if we have a 6-sided die, knowing that our outcomes are 1 through 6. And we're going to have to assign the probability to each of the possible occurring outcomes. So in the box below, I have an example of how this can be done for a coin. Here I'm on the top row, I'm listing my potential outcomes. I have here my outcomes, I have heads, I have tails. This notation here, S, means the full set. This is all potential outcomes that we can occur in an event. So in the event of flipping a coin, our 2 outcomes are heads and tails. This bottom row here, I talk about the probability. So for heads, there's a probability of 0.5. And for tails, there's also a probability of 0.5. Because in the long run, if I were to flip a coin an infinite number of times, half of those results would be a heads, and the other half of those results would be tails. So out of our set of possible outcomes, heads or tails, if each outcome has a probability of occurring, that's 0.5. Let's cover some other basics. And here we're going to talk about 2 key terms to understanding probabilities of multiple events. The first term is known as mutually exclusive. And when 2 events are mutually exclusive, this means if event A happens, event B cannot. So if we look at our little picture in the corner here, if we think about A and B as 2 different sides of a coin, if I flip a coin, I'm either going to get outcome A, heads, or outcome B, tails. There's absolutely no way that if I flip a coin and it lands on heads, it can also land on tails. That's just simply impossible. So this is a prime example of a mutually exclusive event. Only one of the two outcomes can occur. So when we have these mutually exclusive events, we can say that all probabilities or all possible outcomes of that event sum up to 1. So again, let's think about our coin toss with our heads and our tails. The probability that when I flip a coin, it lands on either heads or tails is 0.5 plus 0.5 equal to 1. 100% of our outcomes. Because if we have either heads or tails, that's all we're going to get. We're not going to get a 6. We're not going to get go fish. We're not going to get the red M&M. We're only going to get heads or tails. Another way of thinking about the probability of these mutually exclusive events, we know that 100% of the time we're either getting heads or tails, A or B. So one way to figure out the probability of one of these outcomes is to subtract it from the sum of 1. So here in this converse rule, I can think about the probability of a coin landing on heads as the total sum 1, all potential outcomes, minus the probability of the other outcome, tails. So in this case, are all possible outcomes 1 minus 0.5 equal 0.5. So mutually exclusive events. If event A happens, event B cannot. When I think of mutually exclusive events, I like to think of sporting events. Like say when Ole Miss plays football. If Ole Miss is playing LSU, both Ole Miss and LSU cannot both win the game. Only one of them can win the game. Next, another term for understanding different events is independence, or having independent events. And what this means is that the outcome of event A has no effect on the outcome of event B. So here, if we look at our little image in the bottom right corner, we have event A that has a certain probability of occurring. We have event B that also has a certain probability of occurring. But these are two different events. Think of it as flipping a coin and rolling a die. Both of these events are totally unrelated to one another. If I flip a coin and it lands on heads, that has absolutely no bearing on if I roll a die and I get a 6. So for instance, if I get a coin and it lands on heads, it doesn't have an effect on the roll of a 6-sided die. I can still ask and say, well, what's the probability I land on heads? Well, that's again 1 out of 2, or 0.5. I can also say, well, what is the probability I roll a 1 on a 6-sided die? Well, that's 1 out of 6 outcomes, or 0.167. I can then look at the probability of getting a heads and getting a roll of 1 on a 6-sided die. That probability is this intersection right here between events A and B. It's the probability of observing two independent events occurring. So here I can do this by multiplying the probability of each separate event, multiplying the probability of getting heads, which is 0.5, and then multiplying that by the probability of rolling a 1 on a 6-sided die, which is 0.167. And that math then is just simply what it is, 0.0835. At this point, I want to remind you that I have posted another video called Mutually Exclusive Events Example. This also goes into a lot more detail explaining what mutually exclusive and independent events are. And that should give you a better understanding of what these two things mean. Here, again, just a couple things to think about. When you think about mutually exclusive events, think about, say, a roll of a coin or a sports game where you have two teams playing each other. Independent events are two different games. Say you have an Ole Miss Alabama game and an LSU Auburn game. Well, whoever wins LSU versus Auburn isn't going to have an impact on whether Ole Miss beats Alabama. They're two independent, completely separate events. So when we think about calculating probabilities, there's a set of steps we need to take. The first is to list all possible outcomes. So again, if I'm thinking about my coin, I'm going to list out whether I have heads or tails. Next, I'm going to determine all the possible outcomes that satisfy my necessary criteria. So if I'm thinking about the probability of heads, well, I'm going to say, well, what outcomes determine that criteria? Seeing a heads. Third thing I do is I calculate the probability of each of those relevant outcomes. Then, if I'm looking at multiple events or multiple outcomes, I need to determine if these outcomes are mutually exclusive or if they are independent. If they are mutually exclusive, I add up the probability of the outcomes. Again, keeping in mind a mutually exclusive event is one where only one outcome is possible. Or if I have an independent event, I'm going to multiply the probabilities of those outcomes. Again, where an independent event is where one event does not influence the other, or one outcome does not influence the other. So let's look at this step by step with an example of rolling two dice and seeing how we can get a total of 4 across those 2 dice. So here in my example, I have a pair of dice are thrown. What is the chance of getting a total of 4 spots? So if we think about our probability of event steps, if we list all of our possible outcomes, I would look and see what are all the possible outcomes that we can observe on 2 dice. Well, we can observe 1 and 1, 1 and 2, 1 and 3, so on and so forth. We actually can observe 36 possible outcomes. Next, I can determine which possible outcomes satisfy my necessary criteria. So which outcomes of rolling a die, these 2 dice, would satisfy getting a total of 4 spots? Well, here as we see on the screen, there's 3 possible outcomes. I can roll a 1 and a 3, I can roll a 2 and a 2, and I can roll a 3 and a 1. Next, I can determine the probability of each of these relevant outcomes. So each of these outcomes has a 1 in 36 chance of happening. Again, I said there's 36 possible outcomes that you can There are 36 outcomes that you can see when rolling 2 dice, and the probability of observing a 1 and a 3, that's 1 in 36. The probability of observing 2 and 2 is also 1 in 36. And observing a 3 and a 1 is also a probability of 1 in 36. Next step, I need to determine if these outcomes are mutually exclusive or independent. So here are 3 potential outcomes that I can see when rolling 2 dice. Are these mutually exclusive or independent? Well, if I roll 2 dice and I get a 1 and a 3, can I also observe a 2 and a 2? No, I can't. If I've rolled my pair of dice and got a 1 and a 3, that's the only outcome I can observe. It's mutually exclusive. I either get a 1 and a 3 or I get nothing else. Or if I get a 1 and a 3, I can't get a 2 and a 2, and I can't get a 3 and a 1. Okay? So in this case, these 3 outcomes are mutually exclusive. Only one outcome is possible in the event of rolling these 2 dice. So that means in order to figure out the probability of getting these 3 outcomes, I have to add up the probability of each of those individual outcomes. And that's what I do at the bottom line here. I add up the probability of observing a 1 and a 3, and I add to that the probability of observing 2 and 2, and I add to that then the probability of observing a 3 and a 1. In total, this is 3 out of 36, and reduced down is 0.08. And with that, that wraps up this first little tutorial. The next step is going to be for you to practice calculating probability of events on your own using the probability exercise posted to Blackboard. And then when you do so, use this slide with the probability of an event steps to do so.